Notably, he has supervised the research of 12 PhD candidates with 7 currently in progress and 32 MTech scholars. His involvement in various national and international projects has been highly successful. His current research interests encompass a wide range of areas including VLSI design, processor designing, DNN accelerators, fuzzy processors, computer architecture, nanoelectronics, battery nitride-based devices, low-power processor designing, artificial intelligence, and robotic vision. It gives us a great pleasure to have you with us, sir. Now I would like to request Dr. Anubhav Goyal to present the subject to Dr. Sajad. Please, sir. Thank you, sir. Thank you, ma'am. Now I would like to welcome you, sir, to deliver a talk on multifunctional nanoelectronics devices, a novel way to enhance more and low life.
Good morning to all of you. I'm sorry I'm late. So, I will be talking about multifunctional devices. I mean, multifunctional device to make use of valid and alive still go for, we can say, educate more than that. So, this is the outline of my talk. I will begin with design objectives, which we all have to keep in mind while designing things, whatever may be the abstraction levels. Scaling benefits, non-electronic devices. I will be talking about the short channel devices, short channel effects which nanoscale devices currently face, and which have actually stopped further scaling. Then I will be talking about the solution for the scaling, which is multifunctional devices. I will be discussing various multifunctional devices which we have. And finally, I will conclude my talk. These are the design objectives which one has to keep in mind. So we all are designers, engineers who are here. We work at different levels of abstraction, starting from device level, device, circuit, gate, block, and finally architecture to algorithm level of abstraction. So I believe all these objectives are valid at each and every level of abstraction. The first one is compact design. So objective is always to have a compact design, a design which consumes small space. To have large packing density. This is an objective, important objective. So this compact design definitely will result in power and energy efficiency. So the second objective is always that the design should consume small power, it has to be energy efficient. That will give me large battery life because our devices are mostly not battery operated device. Then the third important goal is always to have high speed, have delay as small as possible. Since we go from 1G to another G, we go from 4G to 5G to 6G. So this delay is an important issue which we have to work. And the same is true with the power consumption in these Gs. So a big hurdle is the power consumption which we have to work. Then the functionality. So whatever you are going to design must be now multifunctional. It should not perform just one function. Transistor, just transistor action. Diode, just diode action. So apart from doing transistor action, the device must do directly gate. It must realize a block. It must directly realize even a Boolean equation. So then we have the cost. It has to be as small as possible. A big impact of the noise. It should be as small as possible, means the device technology noise pattern should be large. And the design has to be long lasting, it has to be reliable. So these are the goals which we have to keep in mind while designing our product, starting from device architecture and algorithm level of abstraction. So we have achieved these goals by by scaling the dimensions of the device. The ultimate objective is again speed, power, packing density, functionality, cost, noise, margin, and reliability. Okay, before going for the scaling, we talk about many terms: nanotechnology, nanoelectronics. What actually this nanotechnology, nanoscience, nanoelectronics means in terms of abstraction levels? We have people working at a material level of abstraction. They try to explore, give us new materials which we can use to realize device. So working at a material level, that we can call as a nanoscience. So nanoscience, they work at a material level of abstraction. So we people, electronics people, we generally don't touch the material. We have been given the material and we try to realize our device using that very material. We don't have any control on the material, right? We don't actually create materials. Fine? So working at that level, we call it nanoscience. Then once we have received the material, we have got silicon, we have got germanium, we have got silicon germanium, gallium arsenide, gallium nitride, carbon nanotubes. So once we have the material, we try to realize a device. Okay? And having the goals, the objective which I have mentioned in our mind. So this level of abstraction we call it, device or transistor level, and we call what is being called as a nanoelectronics. So most of us are working actually at this level of abstraction, which is nanoelectronics. Then we combine the device, we get gate, again then block, then system level, then we have the architecture level, and finally the algorithmic level of abstraction. So working at, we do work at all these levels of abstraction, but we have the common objectives, common goals, which I have mentioned. And these goals we have achieved till date by scaling the dimensions of the device, right? So, our first microprocessor, 4004 microprocessor, our well-known 8085 microprocessor, are based on the technology node, micron technology node, 8085 microprocessor, 3 micron technology, right? So it was 3 micron technology node. Now we have the state-of-the-art processors. We have code i9, i7 processors in Intel. The technology node is 22 nanometers, it is 14 nanometers, it is 7 nanometers, and now people are talking about the 3 nanometers. So we have actually shifted from 3 microns to 3 nanometers, right? So it is because of the significant scaling in the dimensions of the device. So scaling is important, and scaling till date has given us a lot. And what we have achieved out of this scaling? The first thing is that space efficiency, starting with the vacuum tube technology. Recall the size of the computer. It was of the size of a building. I have heard that IIT Kanpur, when they got the first computer, it was brought in a big truck, right? From Lucknow to Kanpur. The scaling of the dimensions has given us the computers which we can carry in our hands. Our mobile phones are, sophisticated computing machines now. All because of the scaling. Then the scaling has given us a reduction in delay. The speed of the operation has got significantly. Again, from kilohertz frequency in the earlier microprocessors, now we have gigahertz, right? Then we have got the energy efficiency. Imagine the energy, power consumption by that computer which IIT Kanpur has got, which they have brought on a truck. What was the power consumption? And compare the power consumption with the state-of-the-art processor, right? Significant decrease in the power and energy efficiency. And of course the cost. I don't know the cost of that computer which they purchased, and compare the cost of that computer on a truck with the computers which we have. Significant decrease in the cost, and all has, all these advantages are attributed to the scaling of the device dimensions. But that doesn't mean that we can continuously scale the dimensions of the device to make our, devices indeed invisible. We have devices transistors now invisible. What else can we do? I don't think there's anything beyond being invisible, right? And people are trying to make these, we can say, more and more and more invisible by scaling the dimension. But unfortunately, it doesn't work in that way. So it was actually this Richard Feynman. He has given the direction. He has a dream in 1959. You must have read this, you must have seen this. He has made a statement in 1959 why we mentioned that why not to, write the entire 24 volumes of encyclopedia of ink on the head of the pin. Means he has given a challenge that on the head of the pin, we must be in a position to store the entire, all volumes of encyclopedia in. We have seen encyclopedia, but not our kids. They haven't seen encyclopedia. Okay? So he has shown this challenge. Now we have dozens of encyclopedias stored in an area which is smaller than the head of the state. He has, mentioned a famous statement. There is a plenty of room at the bottom. So what is this plenty of room at the bottom? It means we have to put in a lot of efforts, we have to put in a lot of hard work to realize this. This statement is old. Today a NAND flash of 4 GB can hold approximately 100 to 200,000 pages of text and description. That is roughly 1,000 pages per millimeter square. NAND flash 4 GB. We cannot purchase now that pen drive of 4 GB pen drive. Nobody is going to purchase. If we are getting that free, we are not going to take it because we have now, pen drives available in terabytes, right? So we can't have this 4 GB at all. So Gordon Moore, he has a dream, and Gordon Moore, he tried to realize the dream, right? We all know Moore, a well-known, we can say well-known chip designer. Intel is, it is Gordon Moore's Intel which we see currently, right? So he started realization of that dream. Okay, he has given us 3 statements, well-known statements, which have been called as Moore's law. What are the 3 statements? The first statement is that the transistor count in memory should double in 18 months. The second count is the transistor count in processor should double in 24 months. And the third statement that the foundry cost is bound to increase, is double in 2 to 3 years. That we are observing now. Okay? But we want to keep this valid. It's extremely hard to keep this valid. That double the transistor count in, in case of processors in 2 years, in case of memory in 1.5 years. Again, how can we double? We have to scale the dimensions. Okay? And at scaling the dimensions, reducing the dimensions is double. And if you see, the third statement is about foundries. Their foundry cost is bound to double in 2 to 3 years. And I believe this is the reason that we don't have a foundry in India. Our government is afraid of having, state-of-the-art foundry in India. Because it needs a lot of money. Foundry cost doubles in 2 to 3 years. So if we put in $1 billion, then after 2 to 3 years, the foundry has to realize a different technology node, a scale technology node, and that scale technology node cannot be used with the existing resources. We have to make a lot of change, sophistication in the existing resources. Then only we can realize that future technology. I believe this is the hurdle. And I request my government that they should not be afraid of all these things. Let's have a foundry, start fabrication over here, as chips are the new oil. We import chips for billions of dollars. So spend that money over here, we are going to be exporters in just a few years. So we will recover all the costs, and we will be in a position to have foundries realizing state-of-the-art technology nodes over here in India. Okay, it all started with the bulk technology. You had a well-known MOSFET designed and developed in 1959-60. May I ask you, who is the person who has actually created this, invented bulk MOSFET or MOSFET? We do a lot involved in MOS technology, design a lot of circuits, but we must know the person. Huh? MOSFET. Okay, people working in the MOSFET technology. It is Atala and Kang, Mohammed M. Atala and Kang of Bell Labs. Okay, they have given us the first transistor, first MOS transistor, right? Okay, MOSFET is still there. We do use MOSFET at all levels of abstraction. We realize our circuits, our gates, our blocks, our ICs on MOSFET. But MOSFET has a lot of advantages, particularly silicon-based MOSFET. Metal technology started in 60s, early 60s, and till date working well. So a lot of expertise, a lot of experience has gone in designing and developing MOS technology. It's a metal technology. Low initial cost. All around the globe we have hundreds of foundries which can fabricate MOS technology. So the cost has got significantly increased. So I believe if we start a foundry, let's have a MOS fabrication foundry in India. Then we have a breakdown strength, reasonably large breakdown strength. It is thermally efficient. You can see one of the biggest advantages with the MOS technology is thermal efficiency. But again, we have the problem. We cannot scale it further and further. Realizing nanoscale device with technology node less than 20 nanometers is extremely difficult when we have a bulk technology. Short channel effects are here. Reduce the dimensions, reduce the channel length, we have the dip in threshold voltage. Threshold voltage decreases. So whenever we have a decrease in threshold voltage, we can say that anything can turn on, can turn off a device. So when we have anything turning on, turning off a device, we can say it's not a reliable device. It's a leaky device. So big issue. So we double the transistor count, but at the same time, if our transistors are not reliable, and it's of no use, then we cannot say that we have actually kept MOS alive. What we are supposed to do, scale the dimensions, double the transistor count, but at the same time the transistors must work efficiently. If they are leaky, then what's the fun of having such transistors? So with bulk technology we have this problem. We have short channel effects. Now we have to go for the alternative, better solutions. The better solutions we can have silicon on insulator, SOI technology. We have fully depleted, we have partially depleted SOI devices. Lot of advantages in general with SOI devices. The biggest one is for a thin film SOI. See, for a thin film SOI structures have best SC suppression. So we can scale thin film SOI further and further and further. Other advantages are we get high speed, large packing density. And this SOI technology has addressed one of the biggest problems with the bulk, that is latch up in CMOS. That has got addressed by SOI technology. Right? We have many more advantages. But we do have drawbacks also. To realize a bulk transistor, we need just one wafer. Okay? But on the other hand, if we have to realize an SOI structure, we need two wafers. We have to bond, and then we can realize that. We have to realize the buried oxide. So after realize the buried oxide, have vapor oxide, bond. This is one way. Similarly, we have other ways also. Okay? But the number of wafers needed to realize an SOI wafer is 2. Okay? So the vapor cost is going to double. Starting with a cost which is double, then the bulk will ultimately result in higher cost. And another problem is that it is thermally inefficient. So we have buried oxide inside, thermal efficiency is poor. Okay, so whatever heat gets generated inside, it is very difficult for that heat to get dissipated. So it's a problem. So we have heat source inside, continuous increase in heat. Then that is going to increase the temperature. So temperature has effect on everything. Right? For example, on metallic interconnections, we wish to have conductivity large, but when there is increase in temperature, that conductivity is bound. So we have decrease in R. We have decrease in conductivity, increase in R. Increase in R will result in increase in delay. Right? So we have C is continuously increasing. We increase transistor count, we increase number of interconnection, we increase that parasitic capacitance. Okay, so we have a continuous increase in C, but this temperature is increasing R also, R of the interconnection also. So we have continuous increase in delay, right? So as I mentioned, that objective is to achieve high speed, small delay. But when we scale the dimensions of the device, we have, for example, these thermal issues. They actually get, you can say, thermal issues, then temperature increase, then R increase, then RC product increase, then delay increase. This is the reason that in the last few years, we haven't seen any significant increase in the speed. You know, I believe from 2010, we have seen that processor speed is around 2 gigahertz. Okay, go to Nano, please purchase the state-of-the-art, a laptop. You will be having speed at 3 gigahertz, 3.5 gigahertz. We haven't got that significant jump, quantum jump in speed. Why is it so? It is because of all these things. We scale, we try to make devices small to achieve high speed, but we have other problems coming in, big issues. Okay, so these are the short channel effects. So if you see here,
It can work as a slide advancer, but it is not, the screen is not connected to the laser.
oh,
It works under.
can I point? It's not pointing.
The laser will not be detected by the screen, so it can work as a slide advancer.
Oh, no. Okay, so we have the short channel effects as you see from the plot. When we reduce the dimensions, when we reduce the channel length, we have a dip in threshold voltage. This should not be there. This we try to actually prevent. We want to have that threshold voltage more or less, it should remain constant. Okay, then only we can have device in control. But unfortunately, in scaling, we have that dip, which is VTH rule of short channel. These are the factors. We have charge sharing. I'm not going to explain this. Charge sharing is there. This is contributing to this VTH. We have drain-induced barrier lowering, barrier on the source side that gets reduced by drain voltage. So that is contributing to that VTH. We have subsurface punch through in the belly of the structure in the substrate. Again, this is contributing to the threshold voltage on SCs. Okay, so we have, proposed a solution a few years back. We have proposed partial ground plane based MOSFET on selective buried oxide. So this structure, it is an SOI structure, but since SOI has the problem of thermal inefficiency, so a window has been created in the oxide. It becomes a cell box, selective buried oxide. But again, this structure then loses that SCA suppression which a thin film SOI structure has. So to address that problem, partial ground planes, heavily doped regions have been realized under the oxide near the edge of a source and drain. So ultimately this structure we call it as partial ground plane structure. This structure has suppressed SC significantly. So we have observed that it is suppressing SC even better than a thin film SOI. And at the same time, since we have the opening in the buried oxide, that opening has improved the cell heating, right? So whatever heat gets generated inside, that now gets easily dissipated through that opening to substrate and the place. So heat dissipation problem has got addressed, and at the same time, we have a better SC suppression. So so this is what I said. Now the thing is that advantages are there for a SOI structure. As I mentioned, that thin film SOI has the best SC suppression. So we have that thin film. It is giving me best SC suppression. But on the flip side, we have the issue. It is thin film, the source drain series resistance. That increases significantly. It's a problem. So source drain series resistance is a problem, and at the same time that realizing a thin film is again a problem, right? So that source drain series resistance, we need to reduce this, eliminate the source drain series resistance. So how can we eliminate it? We can make from fully depleted to partially depleted, but partially depleted is more or less above. So SE separation at par with above. So we can go for that. So we have to search some of the other alternatives. The alternatives are, we have an alternative, we can raise source and drain. This is an alternative to reduce that source drain series resistance. But again, raising source and drain regions make the process complicated. It increases gate to source and drain capacitance. So complicated process and the increase in gate to source and drain capacitance ultimately has an impact on power efficiency and speed. So both the things are there, trade-off is there. And we had a better solution. Better solution is that instead of using doped source, doped drain, we can go for metal source drain MOSFET technology, where we can realize source and drain by metal equations, right? There's a statement: metal source drain technology significantly reduce series resistance problem and hence SCs. The ITRS target six-side series resistance is 8.7 at LG 70 nanometers, increasing to 14.9 units at LG 9.7 nanometers. So see here the difference. From 17 to 9.7, almost half. This has around doubled. The source drain series resistance has doubled. So we have to address this problem, and the solution is in the form of metallic source and drain, employing metal source and drain. We have the advantages: planar structure compatible with CMOS if we go for metal source and drain, and at the same time we replace a doped region by metallic regions. So definitely the source drain series resistance is bound to decrease. The advantage. Atomically abrupt. We need abrupt junctions. In a nanoscale device, we need abrupt junctions. The need of the art is to have abrupt junctions. Okay? So when we dope the impurities, realizing the abrupt junction is difficult. Okay, we have scattering here and there. But if we realize, instead of using a doped region, if we go for a metallic source and drain, we can easily realize that abrupt junction. So this is the advantage. No latch-up effect. So the latch-up effect in the conventional CMOS technology can be addressed by using metal source drain MOSFET technology. Again, then we have a fabrication related issue. So if you realize a doped structure, the temperature requirement is always high. On the other hand, realizing a metallic source and drain, it is a low temperature process. Alright, and again it provides improved leakage current. But again, we have on the flip side, we have the problem with these metal source junctions. That is the on current. On current is not at par with the conventional technology. So if you focus on the on current, try to improve the on current, we can have a better structure than the conventional MOSFET structures. Till date we have been using impurities, we dope impurities, we create source, drain, halo implants, PGPs by doping impurities, by having the conventional ion implantation and diffusion. But when we have the nanoscale device, a nanoscale device faces a lot of issues, right? We cannot realize that short fraction. Diffusing impurities or ion implantation is challenging at nanoscale. So these are the challenges. Formation of junction with extremely high doping gradients is extremely sharp junctions. And again, as I said, source drain series resistance in case of doped structures is a big issue. It continuously increases. At nanoscale, a dopant concentration avoids solid solubility limit. We have to realize a small resistance that generally is being realized by doping impurities, increasing the impurity concentration. But again, how much increase? to what extent we can go to increase that doping concentration, right? Again, we have a challenge over here that we cannot have doping concentration more than solid solubility limit, right? We have silicon, we can dope impurities, for example, boron, to some extent, to some limit. We cannot cross that limit, which is the solid solubility limit. So again, this is a challenge. Then we have another challenge is about controlling the doping concentrations, doping types. Then we have the biggest issue is random doping fluctuations. So when we deal with a dope structure, we have random doping fluctuation issues. So when we have random doping fluctuation issues, that has direct impact on the threshold voltage. So ultimately, threshold voltage is changing. We can say it's not a lab operation. And then we have some structures. For example, we try to shift from silicon to gallium nitride, gain devices. A lot of people do work, but we have, for example, n-type gain is okay. We have realized n-type gain, it is there. But if you want to realize a CMOS type of structure in gain, you need a P gain, right? But realizing a P gain in gallium nitride is extremely difficult. It's not just like the silicon. This is the reason that replacing silicon by other wide bandgap materials, gallium arsenide, gallium nitride is difficult. In gain case, realizing a P type, then realizing the CMOS type of structure in gain is difficult. Charged plasma concept, maybe you may have, you may be knowing this charged plasma concept. So with doping, we have a lot of issues. With the conventional doping, a lot of issues are there. Okay, so how to address the problem with the conventional dope structures? So, these issues are attributed to doping or ion implantation, diffusing impurities. Okay, so we have the solution. The solution is charged plasma devices. In the charged plasma device, we don't perform any conventional doping or ion implantation. We have, for example, silicon, intrinsic silicon layer. In that intrinsic silicon layer, without doping impurities, without diffusing impurities, we do create N positive, P positive, N type, P type, N negative, P negative. So, no doping, no diffusion is involved. Right? No doping, no diffusion is involved. It means all the drawbacks of doping and ion implantation involved. The problem addressed. And the concept is charged plasma concept. In the charged plasma concept, we actually deposit metallic layers of some unique work function. Okay? On the metallic layer, that metallic layer is going to create, is going to you can say diffuse impurities in the silicon. Though there is no diffusion, there is no implantation. Okay? So under the metallic layer, you will see N type, N positive, N double positive, all depending on the work function of the metal. So when you change the work function of the metal, you will actually see the concentration of the dopants under that metallic work function is changed.
Sir, how they are induced? How they are induced by changing the work function by putting the metal of different work function?
First thing is that there is no conventional, induction or diffusion or ion implantation, right? If you see here, I think I have drawn the band diagrams. Can you look at the band diagram? Okay, so band diagrams are there, two band diagrams. One band diagram shows us the realization of electron plasma. On the left hand side, we have electron plasma. On the right hand side, we have hole plasma. What is the condition? As I said that all metals with all work functions cannot induce. They may induce, but that efficient induction, we need something significant. Okay, so that cannot be induced by all metals. We have to select a metal of a particular work function, right? And that work function has to follow the band diagram which is over here. I have shown the two band diagrams, right? So over here, on this side we have the metal, on that side we have the semiconductor, right? And then having a particular, work function and satisfying this condition, right? So this is the condition. If this condition is satisfied by a metal, you will see electron plasma gets created over here. This is being plasma, and remember, this is not that plasma which you have heard about charged plasma, electricity passing through the gas and breaking into ions, it is not that plasma, right? So don't get confused. So it has been given the name as plasma, though it is not that plasma. You have N-type over here just by band bending. You know, band bending you must have seen in case of MOSFET, right? How the electrons get accumulated and we have N positive, P positive. So the same thing is being realized over here by changing the work function of the metal. So when we change the work function and having this relation, this getting satisfied, you get N-type plasma. Similarly over here again a metal of different work function because you have realized of P. Satisfying this function, you will get a P-type plasma. Okay, so this way we can actually create N plasma, N-type concentration, P-type concentration just without doping, without ion implantation.
Sir,
Yes.
So
So
under
for
which
silicon,
physical,
what type of metal we use? Fabricating this, what type of metal we use in case of silicon?
In case of
Silicon.
a lot of metals up there. If you see over there, what is that? That is actually, see here, this is an SOS structure. It is substrate, this is buried oxide. This is silicon film, right? So here, palladium metal have been deposited over here. We have erbium metal over here, right? So this one, this has actually induced N-type plasma over here, and this has induced P-type plasma over here. So we can say here, in this part we have N plasma, in this part we have the P plasma, right? So when we have N plasma and P plasma in close contact, so what has been created? A diode. In a diode we have N positive and P. And the N and P has got realized by diffusing impurities, right? We diffuse impurities N-type. We diffuse impurities, for example, boron has been diffused, it will give me P-type. And what to diffuse to create N-type? N-type dopants. Arsenic, right? So diffuse arsenic we can have N-type, diffuse boron we can have P-type in the conventional technology. But over here you will not see any diffusion of impurities, ion implantation, nothing like that. Have a metal satisfying this condition, over there palladium is there and erbium on the other side is there. So these two metals are going to induce N-type plasma, P-type plasma, and ultimately that top one is a PN junction diode, right? And similarly we have here the lower one is a transistor, right? So that this B. Radhakrishnan,
so why,
he has actually realized this structure.
so why it is called plasma then if it is not ionized here?
Pardon?
Why it is called plasma induced charges if it is not ionized here?
See, first thing is that it is not highly ionized state. Now the question is that why it is being called as a plasma, alright? It has been just given the name plasma. Otherwise people do call it by other names also. Electrostatic doping is also, the same thing, right? So it has been given the name plasma. For example, the person, this one Rajesh Karan, he has given the first diode, right? So he has given the diode, before this one more guy, he has, a similar thing. So they have given the name as plasma, though this is not that plasma.
So how we calculate the junction potential in this?
How to calculate junction potential?
Because when we have a N-type plasma, P-type plasma,
Okay.
then there will be a junction.
Fine.
Then how we calculate the potential at the
See, the thing is that you have palladium and that is diffusing, that is creating N-type. Over there you have erbium and that is again giving the P, right? In the conventional you have N, you have P. The N has been created by diffusing impurities, P has been created by diffusing impurities, right? So what is the similarity in this structure and a conventional structure? Is there any similarity?
there is a doping density of
The similarity is that this is PN structure and that is again a PN structure. The difference is actually realizing P and realizing N. This is the difference. The rest of the things, the models are going to remain same. So whatever technique or technology you have used in computing the potential and other things in the conventional PN junction, the same thing over here. Only what we have done, we have realized N and P by a different method than doping and ion implantation. So there is going to be no difference in the modeling right? If you have a cut line, for example, you design this structure. We design this structure in Selvaco Centaurs. Have a cut line. You will see N type, you will see P type, you will see everything. And if you realize the same structure or the same topic concentration using conventional technique, you get similar things with it.
But
There is no change in the body.
difference in the depletion length. No? Because there we have a lattice structure, then we have a defined depletion rate. But in this case, we does not have a lattice structure proper for the row diagram. So
How can you say that we don't have? Are we changing something silicon? Silicon properties? Nothing, not at all. See, over here we have silicon. In the conventional we have silicon as substrate. The difference lies in just doping impurities. In the conventional case we diffuse, we ion implant it. And we have N, we have P. In this one the same thing, but the difference. So if you see the basic structure is same, this is same. This is, for example, silicon over here, crystal structure is same. There is nothing changed in that. We haven't changed. We have just, this part has doped impurities. So this is N positive in silicon, this is P in silicon. So conventionally we have N in silicon, P in silicon by diffusion and ion implantation. So the difference lies only in realizing N and P. So why we do this? Because with the doped structures, as I mentioned, I have given a lot of drawbacks. Okay, so that drawbacks get overcome by this technique. Okay, so on the so you have a diode over here which is charged plasma based. Then you have a transistor, PNP transistor again, charged plasma. Lot of structures, novel structures have been realized by using this the concept of charged plasma. This is our structure. We have proposed this structure a few years back. Charged plasma based Schottky barrier MOSFET. Now we have Schottky barrier MOSFET, right? Schottky barrier MOSFET in conventional technology, conventional doped structures, we have Schottky barrier. But the same type of structure again can be created by using charged plasma concept. Or we can say the problems in the conventional Schottky barrier. As I said, when we have metal semiconductor, advantages are here, but the biggest drawback is the on current. On current is a problem in case of metal semiconductor structures. How to address that on current? How to enhance that on current? So that on current enhancement can be done by using the concept of charged plasma. Over here we have proposed a structure over here. Unfortunately, this is not working. So this is undoped silicon. This is metal source. Right? So here we have the problem of on current is related to this junction. Right? So that problem has been addressed by using a metal source over here. This metal source will induce a charged plasma in this part. Right? So with the result, in a metal source we have the problem of on current, and that is attributed to that. It is attributed to what? When we have metal semiconductor, we have on current issue. It is attributed to why we have the on current problem in metal semiconductor?
ambipolar.
Oh, ambipolar. Do we have some width over here? Okay, this one. This width. Yeah, you can see this. This is because of the metal. We have this fixed, right? A problem. This barrier is fixed, and this barrier cannot be, decreased by applying the voltage. Or we can say that with VGS we have a little impact over here. This barrier, we wish to have this barrier as small as possible. That is why we have to select appropriate metals. We cannot reduce this barrier by applying VGS. Or we can say that the impact of VGS on this barrier is insignificant, unlike conventional. So problem over here. So this barrier can be addressed by selecting a proper metal, right? So we cannot have any metal. We have to select a metal which will give me this barrier as small as possible, because this barrier cannot be reduced by VGS. Now the problem is on current is actually this barrier over here, the width, right? So this width has to be as small as possible. So how can we make this width as small as possible? We actually use source extension, metallic source extension. This has induced charged plasma over here. That induced charged plasma has actually reduced this width, which you can observe over here. This is the conventional one, blue one. Large width, overall current. So the on current has got significantly increased by having significant reduction in the width. And that significant reduction in the width has been achieved by having here a metallic source extension inducing charge plasma. So you can see the results are, obvious over there. You can see here ID current has got significantly increased, and that has given me cutoff frequency, and of course we have got a decrease in delay. Again, this is being attributed to employing the concept of charged plasma at a very critical area. That's what the function where we have the problem. And similarly, this is a similar structure where we have used charged plasma. We have used a couple of source extensions were here, and in that structure at 4 places to again address the same problem. To address the all current problem, to have an increase in cutoff frequency and other performance. But now, can you give me the? With this type of structure, advantages are here. What's on the flip side? We have got the advantages at the cost of complexity. Alright? Structures are not easy to fabricate. Structures are very much complex. Okay? So having these 4 extensions is not an easy thing. We are unable to fabricate the conventional simple MOSFET. How come this type of structure can be fabricated? So that's a challenge, right? But I do believe the fabrication is improving, fabrication techniques and technologies are improving day by day. So hopefully such complex structures are no more complex in future. Again, a structure which is directly modulated source engineered charged plasma. Again, the concept of charged plasma has been used over here to realize a biosensor over here. And a significant improvement in performance has been achieved. Tunnel free defect another structure. A lot of work is going on in defect. Right? MOSFET, lot of advantages. It has been serving us since decades. But again, the problem with the MOSFET is that we cannot scale it further and further and further. So we are searching alternatives, lot of alternatives. This is an alternative, one of the alternatives. In case of conventional MOSFET, we reduce the barrier, push the barrier, so that we have the charge carriers overcoming the barrier from source channel to drain. It is just pushing, thermal push, right? But that has given us a limit. Okay, that has given us a limit of 60 millivolt per decade, subthreshold slope. S. We can't break that limit in case of conventional MOSFET. Alright? So 60 millivolt per decade is the limit in case of conventional MOSFET. So it means we have to spend 60 millivolt to get that 1 decade change in drain current. Fine. So we have some finite. If you see the characteristics of this structure, this is structure conventional MOSFET. So we have the intercept over here. The intercept over here gives us a leakage, right? So in case of the conventional MOSFET, we have that intercept. It is large. Devices are leaky, particularly the nanoscale device. So problems are there. So problem is attributed to S. How to address the problem? The problems have been addressed by realizing a different structure, which is being called as therapeutic difference. In the conventional thermionic emission, overcome the barrier. In case of PFET, it is not thermionic emission. There is no need to overcome, jump over the barrier. It is just tunnel through the barrier, right? So when we say tunnel through the barrier, so we have a tunnel. Then only we can have the on current. Charge carriers have tunnel. All right. So in case of tunnel, we
what is the minimum width after which the electrodes start tunneling?
Pardon?
What is the minimum width of the band after which electrons start tunneling?
What is that?
Minimum width. Minimum width as we apply the voltage, the bands start moving downwards.
Okay.
And what is the minimum width after which the electrons start turning? Minimum width.
Minimum width.
Hanji.
See,
Band gap.
you are showing me something
Minimum
like
width
this.
of the band gap.
Band gap.
Band gap.
Sit down.
Yeah. Can you ask me?
So, what is the minimum difference between the bands when there is the start of a tunneling?
So where you have put that yellow arrow, what will be
Yes.
the minimum width of that?
Okay. You are telling me this thing, right? See here. What is our objective? See. MOSFET has the issues, but we are getting the best on current. Where large. I don't think. In case of tunneling, subthreshold slope is, the barrier has been reduced, broken. Okay, the limit 60 millivolt is not here. We can have 10 millivolt per decade, we can have 5 millivolt, and it's fabricated device in that range. So when we have subthreshold slope very sharp, it means this type of structure, tunnel defect, is approaching to an ideal switch. In an ideal case, we have sharp. We have subthreshold slope 0. Slope is ideally infinite, S is 0. That's an ideal case. Now the thing is that how to realize what you are saying over here is that what is the minimum, right? You tell me. For example, you design a defect. Okay, what is the objective? Objective is to address the problem of the defect. Defect has lot of advantages, but at the same time it has the biggest advantage, drawback of poor on current. Right? It has the biggest drawback of poor on current. And you know that on current is being attributed. What is the source of the on current? The source of the on current is this overlap. Okay? So when we apply a voltage, we can make this move downwards, we can make it move and then upwards, right? Now the thing is that we have a minimum. You apply a voltage over here, sort of threshold voltage. So you apply a voltage, it will start moving up and down, right? Now, what is our objective? Objective is that the overlap should be as high as possible. You have so that you have the maximum tunneling.
If we have maximum overlap, but
Yeah.
the width of that band gap is high, then also there will be tunneling. If we have maximum overlap of band,
See, tunneling has to be from this band. What is this band?
valence band,
This is valence band. And this
conduction
is
band of channel.
right. So tunneling has to be here. An important objective is that this tunneling area, it should be large. This is one point. And at the same time, this width has to be as small as possible. Right? This is the reason we go for this one. See here.
That I'm asking, what should be the minimum width after which the electrons start tunneling?
So the gap between the conduction and valence band in the horizontal axis.
We have two things. Now we have to overlap the bands, and the second thing, the width should be minimum.
Yeah, width should be as minimum as possible.
Okay, is there any defined gap? The width should be this much, after which electron will start tunneling.
You mean any typical value?
Yes,
Yes.
like 0.2 electrovolt, 0.3 electrovolt of gap.
0.2 electrovolt. The gap has to be as small as possible.
Okay.
Isn't it? If we say 0.2 or 0.3, we have the tunneling, we have still the barrier over there, but then we have to see the magnitude of the on current. What is the preferred value? How much should be this barrier? Ideally, it should be 0, isn't it? Then only we can have it, complete tunneling, right? We should have, between EC and AV, it should be as close as possible. And that closeness is being realized by having, for example, by having dropping concentration, by realizing dropping concentration, or by having that dropping concentration on both the sides as large as possible. The tunnel structures, the tunnel transistors. What's the base of a tunnel structure? The base of the tunnel structure is tunnel diode, right? Tunnel diode. I don't have anything over here. If you recall, the tunnel diode is something like this. Tunnel diode characteristics V and I. Okay. But you want this.
Only one.
So how much should be V over here while you want to have the conduction? Isn't it? Instantaneous. So when we say instantaneous, it means that overlapping has to be as high as possible and that width has to be as low as possible. Alright? So how can I remove this?
Second one.
Last.
Middle one. Middle one.
The center one.
Oh, okay. So it's clear? Fine. So these tunnel field effect transistors, lot of work is going on. First to improve that on current, have it. People are pushing this on current, this to move in the upward direction to reach that conventional MOSFET. So if we are able to realize a TFET with on current at par with conventional MOSFET, right? So it is going to replace, immediately it is going to replace the conventional MOSFET. And at the same time, we have another problem with the TFETs, alright? We have ambipolarity, again a problem over here. So that ambipolarity need to be suppressed. But the thing is that, is this ambipolarity always an issue? Can we use this ambipolarity for something else? For some advantage?
Provide a negative is in a low bias connection.
We people, we design sensors, TFET sensors, right? TFET sensors in on current mode, TFET sensors in ambipolar mode, right? So TFETs can be used as sensors, better sensors in ambipolar mode. So ambipolarity is there, but let us not remove this ambipolarity. Let us use it for sensing, right? So TFETs can sense and they can change that ambipolarity. So if we are getting a change in ambipolarity, we can say that TFETs have sensed something.
But in transistor we can't use ambipolarity.
I'm saying sensors. So sensor, you need a transistor as a sensor, you need TFET as a sensor, but when you need TFET as a sensor, you can use on current for sensing, you can use ambipolarity for sensing, right? So if the object is just sense, a sensor, then TFET in ambipolarity performs well, right? Because that ambipolarity can get changed when the TFET is able to sense the molecules or some molecules. Okay, so we have performed, worked on TFET's objectives. Problems are in front of us, improving on current, right? Suppressing ambipolarity. So a structure has been realized where we have created an inverted C. So this is C. I believe this is C, and this type of structure we created inverted C, right? So this inverted C has actually given me that large tunneling area so that we can have maximum tunneling, right? And ultimately, if you see here, we have got an increase in on current in case of this structure. Some variation in the structure, objective remains same, to have improvement in on current, to have suppressed ambipolarity that we have got over here, which is vertical gate elevator source TFET structure. And this is the structure, though this is simulated, it is not happening, right? This structure is giving us the best ambipolar suppression. Ambipolarity is being fully suppressed, and at the same time there is a significant improvement, increase in on current, and both these advantages have been got independently. Generally what we do something, we get an increase in on current and we have ambipolarity, right? Or we get a decrease in on current and at the same time we suppress ambipolarity. A trade-off type of thing. But in this type of structure, the ambipolarity and on current has got improved independently without any link. And I believe this is the only structure in PCB technology which has ambipolar, where we can control ambipolarity and on current. We actually double, we have got a doubling in on current over here and fully suppress ambipolar in this type of structure. So you can go through this, you can get further details about this structure. Now, since my talk is about multifunction, whether it is conventional MOSFET doped or charged plasma, metal Schottky devices, fully depleted SOI, partially depleted SOI, FinFET, any structure. See, we have multi-gate structures, lot of multi-gate structures, SOI, triple gate, FinFET, bi-gate, gate around, lot of things, lot of structures, individual structures are there. Okay, so we have scaled the dimensions of all these structures. This is what people have been doing. But scaling the dimensions, the structures become complex. We have to search for an alternative. That technology node, it cannot be scaled further and further and further. Right? These are the structures. Some of these structures do exist in our processors, in our mobiles, fully depleted, partially depleted. It is there. We have our mobiles, we have ICs in our mobile based on fully depleted SOI. We have FinFET based structures. Why they have a complex structure? See, look at these structures. They are extremely complex in comparison to bulk conventional MOSFET. But why we go for these structures? As I said, it is short channel effects, suppressive. This is the objective, but extremely. What's an alternative? Need of the art is to have multifunctional structures. Multifunctional structure means, see, for example, in case of an inverter, we need 2 transistors. In case of NAND gate in NMOS technology, we need 3 transistors. In case of CMOS, we need 4. Similarly, AND gate, we need 5, 6 transistors. And when we go for multiplexers, decoders, encoders, right, we have dozens of transistors in these blocks. Fine? Dozens of transistors. Combine these transistors and realize a block. Now the thing is that if we just work at a block level and realize a transistor, single transistor or couple of transistors, we directly gives you an AND action. Conventional technology, 5 transistors. Multifunctional technology, instead of 5, have 1. If we have a 1 transistor and if we have a 1 transistor NAND, if we have a couple of transistor based Boolean equation. You know Boolean equation, we use that T-map. Objective is to realize operations, ANDing, ORing, but still we are left with dozens of ANDing and ORing. But if you enter inside, you will see dozens of transistors. Now imagine a Boolean equation in the conventional technology, which need dozens of gates, hundreds of transistors, is being realized by just 2 transistors. How much saving will be? So this is the concept of multifunctional devices, multifunctional technology. This is the first structure, a single device based inverter. Right? So if you see here, this is what we propose. We are given the name Sajad Schottky device, and fortunately just a few days back we have received the patent for this one, finally granted. So single transistor is there, double gate. It can perform N-type operation, it can perform P-type operation, and it can directly realize an inverter. Normally an inverter we need 2 transistors, conventional. But put here just single transistor, realizing 3 operations. So if you want to realize NMOS, N-type, it can give you N-type, it can give you P-type, and it can work as an inverter. So what we have used over here, we have used again metal silicides, erbium silicide, source drain in N mode, that top one, palladium silicide again source drain in P mode. So in N mode and P mode, we use different metallic layers, metallic silicides, erbium and palladium silicide. Why we use this erbium silicide and palladium silicide? What we have actually looked. Again, we had a problem with this structure. It is on current again, right? So if you see here, we have observed that palladium silicide and erbium silicide or ytterbium silicide results in reduced Schottky barrier heights with silicon. You know, I think you something asked about that. Why we use these metal silicides? For example, erbium silicide, palladium silicide. We can't go for the random silicide. It's not like that. What we have to see, we have to look at Schottky barrier heights with silicon. the Schottky barrier height has to be as small as possible, right? So these two metal silicides actually give us the reduced Schottky barrier height, so that we can have conduction, we can have that efficient N-type, P-type, and inverted action. So this is the comparison. If you see here, our structure and a conventional structure, conventional CMOS. First look at number of regions, number of doped regions. Then look at number of junctions, and look the complete structure, look at interconnections. This is the comparative analysis. Transistor count 2, what there is 1. Junction, see here we have significant reduction in junctions, 9 PN junctions, semiconductor. There is 9 and 3. Number of doped regions. In our structure, we can have 0 to 1. We can have that intrinsic, right? So, 0. So, in the conventional one, 8 regions, 8 doped regions. In the proposed structure, we have just 0 to 1. Substrates, 3 times reduction in substrate was here. So, this has given us a compact structure which directly realize NP and CMOS. Let me skip the operation mechanism. So this is transfer characteristics, output characteristics of this structure. And then analysis. Okay, this is important. See here, I have folded. It appears that in our proposed structure we have folded two metal silicides, and has given me this NP and Ca. Now the thing is that can we realize the same thing in the conventional doped regions? For example, we have doped region here, doped region here. This is N-type, this is P-type, merged it. Okay, can we realize the structure? Then, if we are able to realize the structure by just, folding these, making a contact of these two structures, then it's of no use. But when we fold the conventional structures, we do have a depletion here and here, right? So this is drain, this is drain. In case of CMOS, we have drain connected, right? We have drains connected. In our proposed structure, we have metallic drain, so we have an automatic contact, okay? So, but in this case, if we have doped region, we have a depletion layer, depletion region. So, this depletion region, we have that electric field and that diode type of action. So, we don't want to have a diode type of action or depletion region or break into depletion region, into drains in a CMOS type structure. That's I'm going to pass. Okay, see here, the same structure can be used as a transmission gate. In the previous structure, there was an oxide over here. Oxide over here, eliminate the oxide. This structure will work as a transmission gate. In the conventional transmission gates, how many transistors we need? We need 2 transistors, right? Actually, we need 4, right? We need 4 over here. To realize that, inverted, right? So we need 4. So over here in the transmission part, just 2 transistors, and simple just having, folding up to metal silicides. So this is working as a transmission gate. Now again the comparison over here, that is the conventional one. If you look at the number of interconnections, in the conventional case we do have interconnections, but in the proposed structures we actually save some interconnections. Between drains, we need not any interconnection. Okay, then we can have this is a complete transmission gate, right? In the transmission gate, we need this one inverter to realize pi and fiber. So we can over here use our own proposed structure as an inverter. So the combination of the transmission part and the inverter will realize complete transmission gate. Okay, so this is how we actually realize exclusive or using our technology. Realizing mux, realizing an AND gate. Now this is important. Again, a multifunction. is this one? AND gate. Sorry, NAND gate, 2 input NAND gate, right? 2 input NAND gate, number of transistors 4. We have pull down network, we have series, we have pull up, we have parallel combination. You know, we can realize this type of structure by using gate engineered structures. Alright? Gate engineered structures, it means that if we have to realize a series combination of transistors, 2 transistor series, we can realize these 2 transistors by a single trace, 2 gates, having right split gate. 1 transistor realizing 2 transistors. 1 transistor realizing series combination of 2 transistors.
So what is the minimum length difference between the two gates?
See here, what we have to make sure, for example, you want to have a complete channel. You want to have that this should be grounded, but here output has been grounded. Fine. So this is, for example, metallic path, no problem over here. And what do you want this to be? Electron channel. Exactly. It has to be electron channel, electron layer. Now the electron channel can be created if in one is 1, and you will see over here electron layer. If in 2 is 1, again an electron layer over here. So you have 2 electron layers, right? So you have to design this gap in such a way so that these 2 electron layers make a contact. Okay?
So if one is off and one is on.
Yeah, if one is off and one is on, it means we need not a channel. That you will see. See here. This is NAND gate or not gate? This is NAND gate, right? This is NAND gate. What's the truth table? What is the truth table for the NAND gate? Yeah, you can look at this one. This is 1. This is 1. Output is 1 1 1 0, right? 1 1 0. So this is NAND. 0 1 0 1 0 0
One.
sorry.
Sir, it is coming out.
1 1 0 0 1 1 1 0 1 and 0 0 1. What type of gate is this? It's a NAND, right? Now what you are seeing, so see, you want this to be a complete channel. For this one, the first one, 1 1 0. So if in 1 is 1, in 2 is 1, so this is inducing a channel over here, this is inducing a channel over here. The gap is right so that these 2 channels, electron layers, make a contact. So we have an electron layer over here, a contact over here. So when this is 1 1, so this output through this one gets grounded. Right? Now for example, you have in 1 0 or in 2 0. If this is 0, do you have a channel over here? So there is a break over here. So there is no chance that this output can get grounded. And same is if this is 0, again it can't be grounded. It is 0 0, again the thing it can't be grounded. So for 3 combinations, this output can never be grounded, which is true. It can be observed. But when we have this one and this one, we have a channel over here, so it will get grounded. Now the thing is that what about this one? What about this one? When we have in 1 0, for example, this is 1, this is 0, this is 1, we have a channel over here. So this VDD, this output gets connected to VDD, right? When this is 1. For example, now this is 0 and this is 1. Again, this VDD, it gets grounded. Now this is 1 and this is 1, so we have a full-fledged channel. So we have this VDD getting grounded to it. Right? So this way, this structure can realize the NAND. And I believe this is the norm. Right? The same structure, we have flipped it. Now the interesting thing is that, for example, you need 5 input NAND. So how many transistors you need over here? 5 input NAND, 1, 2, 3, 4, 5. 5 over here, series combination of 5 transistors, parallel combination of 5 transistors, right? Series combination of 5 transistors, parallel combination of 5 transistors means 10 transistors. So what can you do over here to realize just 2 transistors? Realize these 10 The series can be realized by having in 1, in 2, in 3, in 4, in 5. Right? Has split, 4 splits. And over here, you can have the parallel one. Right? Again, perform this splitting over here. Parallel splitting. Splitting over here. So just split the gates, you will realize the series combination. Combination of splitting gates and parallel one, you will realize the parallel combination. Right? This way. What is this? See here. How many transistors? This is exclusive OR gate. The convention 1, 2, 3, 4, 5, 6, 7, 8. 8 transistors. Right? 8 transistors, and over here just split gate. Just we have 2 split gate transistors. Splitting, and splitting a gate is not a challenging task. It's not a big deal. We can easily realize splitting of the gate, and we can realize the switch. Right? And we have observed that by extending this one, we can realize any Boolean equation. Boolean equation of any size. Okay? Boolean equation of any size which normally needs dozens of gates, hundreds of transistors, just by gate engineered these devices, just by 2 transistors we can realize. So this is what the multifunctional technology is all about. Again, this is hybrid one. Over here we can realize gates. We can realize directly gates at a transistor level of abstraction. This is a transistor, it can realize a gate, right? It normally needs multiple transistors. So this is a basic logic gate which we have realized by just single transistor. Okay, so this is all about multifunctional devices. So if we focus on multifunctional devices, means at a device level of abstraction, at a transistor level of abstraction, if we are able to realize efficiently higher structures, then we need not go for the scaling of the device. We can have the micron technology. Even micron technology we can have, and we can realize hundreds of transistors. So in micron technology, if we are directly able to realize a block which conventionally needs hundreds of transistors, it's work. So we don't have any problem, right? So this is why people are going for multifunctional technology now. Now the objective is to extend Moore's law. We want to keep the Moore's law alive, Moore alive, though probably he has died recently, right? So we can keep Moore's law valid for 5 to 7 years if we go for better structures, thin-fed, multiple gates which I have shown. If we go for better materials, strained silicon, silicon germanium, what are materials are available people to use? CNTs, carbon nanotube, organic electronics. So we can keep this alive for 7 to 15 years. See here, this is not based on some experimentation, right? It's an observation. And if we go for new device physics, just like we have Deptt technology, it's a new device physics. We can have Moore's law beyond 15 years. We can have tunnel transistors, neuromorphic, spintronics, new device. But if we go for multifunctional devices, we can keep Moore's law valid beyond 20 years. Okay, so I believe till 2050 Moore's law will be still alive and will be still there, will be still pushing us if we go for multifunctional things. This is what is the target. Okay, target in ICs to have multiple billions of transistors. We do have, right? Our processors have billions of transistors, but do we have some target, some limit? I believe the target is the human brain. The human brain has 100 billion neurons. Neuron is a complex. Each neuron has thousands of snaps, 1,100 billion. Multiple billions, hundreds of billions. Right? So, what we have achieved, the state-of-the-art processor has just 19.2 billion transistors, around 60 billion informations. So, we are not catching up. It is 19.2 and over there it is billions, hundreds of thousands of billions. Okay? So this is what we have achieved. Core I9, 7 billion transistors. We have now the state of the art. The transistor count is around 7 billion. So it may have gone to 7, 9, 10 billion, but it is still very small in comparison, insignificant in comparison to our brain, what we have. So there is no comparison between them. That is why this statement is well known. There is plenty of room at the bottom. So we had to put in a lot of multifunctional, new device technology, new methodology. Objective is to realize the transfer count, realize the computational capability we have in our. Okay, so let me conclude. Our objective is there. First thing is that we have to keep Moore's law valid and alive, double the transistor count, but remember, it is not just doubling. The transistors have work. If we have leaky transistors and we continuously double it, what's the fun? Nothing. Okay, so reliable. Doubling, but at the same time, look at the reliability aspect. Performance. Multiple, SCs have to be suppressed. Lot of structures have been designed and developed. Multi-gate is there, PGP is there, ton structures are there. And the better option appears to be multifunctional structures, realizing blocks, complex Boolean equation at the transistor level directly. Don't go about scaling and then combining and then this and that. But directly realize a circuit, a gate, an IC, a single transistor based processor. Two approaches which we have explored is gate engineer and hybrid group techniques. So I do believe we are able to fabricate these structures and really see the performance and aspect. Do you have any questions?
So your PPT was very nice. I have a question. Can you please roll back?
Huh?
Roll back to the slide. So next. There was this one in which over source and drain there were oxides. My question is that how, if source and drain they are covered with oxide, how are we going to provide the biasing? नहीं आगे. So I think it was last की 5th or 6th from last.
In devices are in multifunctional structures.
The devices.
Yeah? Okay, let me go back. Let me show you from slide first.
So we can start from the last. There was an engineering.
Huh?
We can start from the back. So this. So in this over P plus, in figure C, A, B, C, D, N plus and N plus they are source and drain terminals. This HFO2, do we have a layer of it over the source and drain terminal? And if yes, then how are we going to provide the biasing? Because for make it function, we need to provide biasing at the gate terminals and the drain terminals with respect to VGS and VDS. So my question is, do we have a layer of like HFO2 is a grey color?
Okay.
Is it over the source terminal and drain terminal also? Or they are?
So I think you can see the green over here.
Same.
I think the green is from this point to this. Can you see the green?
Yes. Okay. Now.
So it's visible in D part. Yes, visible in D.
So this is green over here, and there is no green.
So there is no HFO2 over source and drain.
Actually, we need a contact over here, right?
Yes,
We need a
that's
source
what I'm
contact.
asking.
We need a source contact over here.
Yes.
Right?
For providing the biasing.
Yeah. Bias we have to provide. We can provide that bias over here also. Since we have a contact, over here. This is schematic, right? In the design, we can have, for example, if I would have given something like this, right? So.
Nice design.
Okay.
I would love to present a moment to Dr. Sajad.
Okay, mine is nothing but perfect.
Now we have second speaker of the day, Dr. Sonam Tiwari with us. Dr. Sonam Tiwari received the Bachelor's degree in Electronics and Communication Engineering from Kurukshetra University in 2005 and a Master degree in VLSI Design and a PhD degree all around MOSFET from University in New Delhi. In 2012 and 2018 respectively. She is currently working as an assistant professor with the Department of Electronics and Communication Engineering, Very Technological University. She is also guiding 9 PhD students in pursuing their doctoral work under her supervision in the area of semiconductor device modeling and design. She has one published patent, one patent communicated, 5 registered copyrights, 68 publications in reputed SCI journals, and numerous international and national conferences. I would like to call Ms. Neeraj to present the sampling to Dr. Sonam Tiwari. After this, first we proceed for a group photograph, and after that we will proceed for lunch in photo session.
And when is the second session?
After that, the second session will be resumed from 4 o'clock
So right now,
for photograph, group photograph.